Welcome to today's problem walkthrough. We'll be exploring problem number 1704, titled Determine if string halves are alike. In this problem, we'll analyze how to determine whether the two halves of an even-length string contain the same number of vowels. Let's dive in. In this problem, we are tasked with determining if a string's two halves are alike. The string S is guaranteed to have an even length, which means it can be split into two equal parts, the first half, A, and the second half, B. The halves are considered alike if they contain the same number of vowels. Here, vowels include both lowercase and uppercase versions of A, E, I, O, and U. The function should return true if the halves are alike and false otherwise. For example, if S is book, we split it into bo and ok and check whether both halves have the same number of vowels. If they do, the result is true. If not, it's false. The input is always a string of English letters, and the output is a Boolean value indicating whether the halves are alike. To better understand the problem, let's look at some examples. First, consider the input S equals book. Splitting it into two halves gives A equals bo and B equals ok. The first half contains one vowel, which is O, and the second half also contains one vowel, which is again O. Since both halves have the same number of vowels, the function should return true. Now, take the input S equals textbook. Splitting it into halves gives A equals text and B equals book. Here, the first half A contains one vowel, which is E. Meanwhile, the second half B equals book contains two vowels, both of which are O. Since the halves do not have the same number of vowels, the function should return false. Another example is S equals Merry Christmas. Splitting it into A equals Merry C and B equals Christmas, we find that the first half has one vowel, which is E, while the second half contains two vowels, I and A. Because the counts of vowels are not equal, the output in this case is false as well. Now, consider the input S equals A, B, C, D, F, G, H. Splitting it into halves gives A equals A, B, C, D and B equals E, F, G, H. The first half contains one vowel, A, and the second half contains one vowel, E. Since both halves have the same number of vowels, the function should return true. This example also illustrates that the function treats vowels as case-insensitive, meaning uppercase vowels like A and lowercase vowels like A are counted in the same way. Finally, let's review the constraints and some edge cases. The string S will always have an even length between 2 and 10,000 characters and will consist only of uppercase and lowercase English letters. Edge cases to consider include strings with no vowels, such as S equals B, C, D, F, G, H, where both halves have zero vowels, so the output would be true. Another case is when the string contains only vowels, such as S equals A, I, O, I, O, U. Here, both halves will likely have equal numbers of vowels, resulting in true. Remember that the function is case-insensitive, so vowels like A and A are treated the same. These factors should guide how we approach the solution to this problem. To solve this problem, we need to determine whether the two halves of a given string contain the same number of vowels. The vowels are defined as at E, I, O, U and their uppercase counterparts. Since the string is guaranteed to have an even length, we can break it down into two equal parts. The solution involves two main steps: first, splitting the string into two halves, and second, counting the vowels in each half to compare their totals. One straightforward way to approach this is the brute force method. Here, we manually split the string into two halves, count the vowels in each half using a loop, and then compare the two counts. The complexity is linear with respect to the length of the string since we iterate through each character once, and the space requirement is minimal as we only track counters. While this approach is simple and achieves optimal time complexity, it can be improved by leveraging Python's built-in features to reduce verbosity and streamline the implementation. Another way to approach this problem is with the two-pointer technique. Instead of explicitly splitting the string, we can use two pointers, one starting at the beginning of the string and the other at the midpoint. As we traverse the string, one pointer counts vowels in the first half while the other counts vowels in the second half. This method avoids the overhead of slicing the string, which can be beneficial in some environments. The time complexity remains O(n), since we still process each character once, and the space complexity remains O(1). However, this approach introduces some additional complexity due to the need to manage pointer logic, which can make the code less readable. While effective, this trade-off in readability may not always be desirable depending on the context. An optimized approach leverages Python's slicing capabilities for a more compact solution. Here, we define a set containing all the vowels to ensure efficient membership checks. Using slicing, we split the string into two halves. The first half is obtained with s and //2, and the second half with s and //2. To count vowels in each half, we use a generator expression inside the sum function, which allows us to calculate the vowel count in a single line of code for both halves. Finally, we compare the two counts. This approach is efficient, running in O(n) time, and it uses O(1) space since membership checks and counters are constant. The main advantage of this method is its simplicity and clarity. It takes advantage of Python's built-in slicing and generator features for a clean and concise solution. However, this approach is best suited for Python environments and may not translate as effectively to other languages without similar slicing capabilities. For this problem, we chose the optimized counting approach using Python slicing. The even length of the string simplifies slicing into two halves, and using a set for vowels ensures O(1) membership checks. The combination of slicing and the sum function with a generator makes the implementation clean, efficient, and concise. This approach strikes the right balance between readability and performance. While the brute force method is also effective, it is slightly more verbose since it requires manual iteration and counting. The two-pointer method avoids splitting but adds complexity due to pointer management. By comparison, the chosen strategy provides a clear and elegant solution while maintaining the same O(n) time and O(1) space complexity. This makes it an ideal choice for solving the problem efficiently without sacrificing code clarity. To determine if the two halves of a given string are alike in terms of vowels, we start with a structured approach. First, we validate the input. The string must not be empty, and its length must be even. If the length is odd, such as with the string hello, we can't split it into two equal halves, so the problem becomes invalid. Once the input is valid, we split the string in half. Using slicing, the first half is formed by taking characters from the start up to the midpoint, while the second half starts from the midpoint to the end. For example, if the string is bookcase, the first half is book, and the second half is case. This gives us the foundation to analyze the two parts separately. Next, we define the set of vowels to identify them efficiently. This set includes both uppercase and lowercase vowels, a, e, I, o, u, and their uppercase counterparts. Using a set allows us to check if a character is a vowel in constant time. After defining the vowels, we initialize two counters, one for each half of the string, to keep track of the number of vowels. We then iterate through each character in the left half and the right half. For every character, we check if it exists in the vowel set. If it does, we increment the corresponding counter. For instance, in the string bookcase, the left half book contains two vowels, O and O, giving it a count of 2. Similarly, the right half case contains two vowels, A and E, leading to a count of 2. Finally, we compare these two counts. If they are equal, we conclude that the halves are alike and return true. Otherwise, we return false. It's important to handle edge cases to make the algorithm robust. If a string has no vowels at all, the counts for both halves will naturally be 0, which means the function should return true because the halves are still alike in the absence of vowels. Additionally, if the string itself is empty, we should handle this gracefully, either by returning false or raising an appropriate error. Case insensitivity is also addressed by including both uppercase and lowercase vowels in our predefined set. This ensures that the algorithm works uniformly regardless of the case of the input string. Key insights from this approach include the efficiency of using a set for vowel checking, which ensures constant time lookups, and the simplicity of using slicing to split the string, which operates in linear time. These design choices ensure that the algorithm remains efficient and easy to understand. The vowel comparison strategy here is also optimized for simplicity and efficiency. By counting vowels separately for each half and directly comparing the counts, we avoid the need for additional data structures, such as arrays or lists, which could introduce unnecessary overhead. This keeps the algorithm lightweight while maintaining clarity. The data structures used are minimal. We rely on the vowel set for quick lookups, which is highly efficient, and two integer variables for counting vowels in each half. These choices ensure that the memory usage remains low, regardless of the length of the input string. Finally, let's analyze the complexity of the algorithm. The time complexity is O(n), where n is the length of the string. This is because splitting the string into two halves takes O(n), and iterating through each half to count vowels also takes O(n). The space complexity is O(1), as the algorithm only uses a set for the vowels and two counters, which do not scale with the size of the string. This makes the solution both time efficient and space efficient, capable of handling even long strings without consuming additional resources. This solution determines whether the two halves of a given string are alike, meaning they contain the same number of vowels. Here's how the code works step by step. 1. We define a class solution with a method halves are alike. 2. Inside the method, we first define a set vowels containing both uppercase and lowercase vowels, a, e, I, o, u, for easy membership checks. Using a set ensures that vowel lookups are efficient. 3. We calculate the midpoint of the string s using len s //2. This is possible because the problem guarantees the string length is always even. 4. We count the vowels in the first half of the string (n) using a generator expression inside the sum function. The expression iterates over each character in the first half, checking if the character is in the vowel set and adding 1 for each match. 5. Similarly, we count the vowels in the second half of the string (n) using the same approach. 6. Finally, we compare the vowel counts of the first and second halves. If they are equal, the method returns true, otherwise, it returns false. This implementation is efficient, as it iterates through the string only once per half. The time complexity is O(n), where n is the length of the string, and the space complexity is O(1), since no additional data structures are used beyond the vowel set and a few variables. This is the Java implementation of the problem determine if string halves are alike, LeetCode number 1704. The logic mirrors the Python solution, using a hash set for efficient vowel lookup and a single loop to count vowels in both halves of the string. Key differences include type declarations and the use of Java-specific collections like hash set. Here, we start with the input string s, which is book. The first step is to initialize the set of vowels, both uppercase and lowercase, so that we can easily check for membership later. Then, we calculate n, which is half the length of the string. This gives us the split point to divide the string into two halves. For the first half, we extract the substring bow. To count the vowels in this half, we use a generator expression that checks each character against the vowel set. For B, it is not a vowel, so the count stays at 0. For O, it is a vowel, so the count increases to 1. This gives us a first_half_ count of 1. Now, we move to the second half of the string, which is OK. Again, we use a generator expression to count the vowels. For the first character O, it is a vowel, so the count becomes 1. The next character, K, is not a vowel, so the count remains 1. This gives us a second_half_ count of 1. Finally, we compare the vowel counts of both halves. Since first_half_ count equals second_half_ count, which is 1 equals 1, the result is true. In this example, the input string is textbook. We still use the same set of vowels and calculate n as half the string length, which is 4. This splits the string into text and book. For the first half, text, we count the vowels using a generator expression. The letter T is not a vowel, so the count remains 0. The next letter, E, is a vowel, so the count increases to 1. X and the second T are not vowels, so the count stays at 1. This results in a first_half_ count of 1. Next, we focus on the second half, book. Using the same approach, we iterate through each character. The letter B is not a vowel, so the count remains 0. The first O is a vowel, so the count becomes 1. The second O is also a vowel, so the count increases to 2. The final letter, K, is not a vowel, so the count remains 2. This gives us a second_half_ count of 2. When we compare the counts, first_half_ count is 1 and second_half_ count is 2. Since the counts are not equal, the result is false. Here, the input string is ABCDEFGH. We still use the same set of vowels and calculate n as 4, which splits the string into ABCD and EFGH. For the first half, ABCD, we count the vowels using a generator expression. The first character, A, is a vowel, so the count becomes 1. The next three characters, B, C, and D, are not vowels, so the count remains 1. This results in a first half count of 1. For the second half, EFGH, we count the vowels in the same way. The first character, E, is a vowel, so the count becomes 1. The next three characters, F, G, and H, are not vowels, so the count remains 1. This gives us a second half count of 1. Comparing the counts, both halves have a vowel count of 1, so the comparison first half count equals second half count evaluates to true. Thus, the output is true. In this problem, the time complexity of the solution is determined by how the operations scale with the length of the input string, denoted as n. First, calculating the length of the string using Python's len s function is an O1 operation since the length is internally stored as a property. Next, the string is split into two halves using slicing. Each slice operation involves copying elements proportional to the size of the slice. Since the string is divided into two halves of size n/2, the total cost for slicing both halves is O n/2 plus O n/2, which simplifies to O n. Finally, for counting vowels in each half, we iterate through all characters in the respective halves. Checking whether a character is in the vowel set is an O1 operation, and summing these checks for n/2 characters in each half results in O n/2 plus O n/2, or O n. Combining these steps, the total time complexity is determined to be O n. After determining the time complexity of slicing and counting vowels, the comparison step, where we check if first half count equals second half count, is a simple equality check and takes constant time, or O1. Since the slicing and vowel counting steps dominate the runtime, the overall time complexity remains O n. Moving on to space complexity, the solution uses a fixed set to store vowels, which requires a constant amount of memory, or O1. When slicing the string into two halves, Python does not allocate new memory but instead references portions of the original string, meaning no additional space is consumed. This ensures the slicing operation only affects time complexity and not space. In addition to the vowel set in string slicing, we use two integer counters, first half count and second half count, to keep track of the number of vowels in each half. These variables require constant space, or O1, as they do not scale with the length of the string. Since no other data structures are used, and all operations are performed in place or with constant memory, the overall space complexity is O1. To compare, a brute force approach might involve storing characters from the two halves in separate lists, which would require O(n) space for the additional storage. While the time complexity of both approaches is O(n), the brute force method introduces unnecessary memory overhead, making it less efficient. The optimized solution avoids creating additional data structures, processes the string in place, and ensures that all operations are performed with minimal memory usage. This makes the approach efficient in both time and space. Analyzing the best, average, and worst-case scenarios, we see that the time complexity remains O(n) in all cases. For an even-length string, splitting it into two equal halves is straightforward, but this does not reduce the number of operations required. Similarly, for an odd-length string, slicing internally handles uneven division, and no extra complexity is introduced. Thus, regardless of the input string's length or structure, the time complexity consistently remains O(n). To mathematically confirm the time complexity, we consider the key operations performed. Slicing the string involves two operations of O(n/2), which combine to O(n). Counting vowels also involves two operations of O(n/2), which again sum to O(n). Other operations, such as calculating the length of the string and comparing the vowel counts, are constant time operations, or O1. Adding these together gives O(n) plus O1, which simplifies to O(n). This reaffirms that the overall time complexity of the solution is O(n). When working on this problem, there are a few common mistakes to watch out for. First, ignoring case sensitivity can lead to errors, as it's easy to check only lowercase vowels like at E, I, O, U and overlook their uppercase counterparts. A simple fix is to use a set that includes both cases, or you can convert the string to lowercase before processing. Next, splitting the string incorrectly is another frequent issue. If the string isn't split into exactly two halves, the comparison will fail. To avoid this, ensure you explicitly split the string into the first half using s and //2, and the second half with s and //2, where n is the length of the string. Another potential pitfall is counting non-vowel characters. Using methods like s.count, without filtering for vowels can lead to incorrect results. Instead, iterate through the string and count only the characters that belong to your vowel set. Lastly, some solutions assume the input string will always have an even length. This can cause runtime errors if the string length is odd. To prevent this, add a simple check at the beginning to ensure the length of the string is divisible by 2. Now, let's look at a few additional tips and insights. Inefficiently iterating over the entire string is a common performance issue. Instead of processing the full string, focus only on the two halves. This optimization reduces unnecessary operations. In interviews, breaking a string into meaningful substrings and processing each part based on specific criteria is a key pattern to master. Interviewers often want to see how efficiently you can iterate through subsets of the input. Be mindful of edge cases, such as an empty string, strings with no vowels, or strings where vowels are repeated. For optimization, aim to use constant space by maintaining 2 counters for the vowels in each half, avoiding extra data structures unless absolutely required. Lastly, communication is critical. Always clarify assumptions with your interviewer, like whether the input is guaranteed to have an even length. This can save you from unnecessary confusion during the implementation phase. To further strengthen your understanding, here are a few related problems. LeetCode 125, valid palindrome, involves string manipulation and can help reinforce foundational skills. LeetCode 344, reverse string, and LeetCode 345, reverse vowels of a string, are both great follow-ups that focus on string traversal and vowel-specific operations. LeetCode 409, longest palindrome, is another interesting problem that dives into character frequency analysis. In terms of alternative approaches, you might consider using a two-pointer technique. This involves one pointer starting at the beginning of the string and the other at the middle, counting vowels in each half simultaneously. While this can save computation, it requires precise index handling. Another option is to pre-process the string using a vowel map. By marking vowel positions in advance, you can optimize lookup during counting, though this comes with slightly higher space usage. Finally, you could use regular expressions to match vowels in each half. This approach is concise and easy to implement but might be slower due to regex overhead, especially for long strings. Each of these approaches has trade-offs, so choose the one that best fits the problem constraints and your familiarity with the techniques. Great job completing the problem. To summarize, we compared the number of vowels in 2 string halves using an efficient algorithm with linear time complexity. Remember the key takeaways about string traversal and breaking problems into manageable pieces. Thanks for tuning in. Be sure to like and subscribe for more problem-solving sessions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!